pay attention to what's significant about here the numerology about today's date?
It's a palindrome.
It's 2/22/22.
How? Yeah, if you use
Somebody
the
called that to my
regular
attention
system,
earlier
22
today.
2022.
This only happens once.
22nd day of
It
February.
won't happen again for 100 years. We'll wait for the next one. Get to 3, 30, right? Can't get to 30. So happy TWO, happy Tuesday. Okay. And it's, of course, pouring rain out there, thundering in the middle of February. But, so this will be the last bit of new information that you will need for the exam that's scheduled for next Tuesday. Okay? On Thursday, we'll basically do a review of the material. I'm going to use a Socrative format where I can project questions up on the screen and you guys will get to answer them using a device. So nobody will know who you are. You don't have to say anything. You just have to move your fingers or your thumb. And we'll see how well you're mastering some of the material. It'll also give you kind of an idea of where you stand and maybe what you should be working on over this weekend before the exam on Tuesday. We will again use the Carmen quiz format. I'll have a passcode to open it for you when you get here. I think that worked out pretty well last time. Certainly got feedback from you guys a lot faster than if I had to manually grade 130 some paper copies. Okay? So, the last lecture, we did talk about the conduit function of the brainstem, how things get from point to point, and we focused on how sensory information, namely touch and pain, got to the cerebral cortex for awareness, for localization, for figuring out how intense a particular stimulus is. So today, we're going to shift and we're going to talk about descending pathways, which means how do neurons in the cortex, the brainstem, control neurons that are at the level of the spinal cord, our motor neurons that are going out to innervate our muscles. Okay, objectives. Let me just point out, I was just looking at these. Disregard number 6 for now. I changed a few things, so you don't have to do objective 6 until block 3, and then I'll reintroduce it. I'll send you an email also so that you want to hear do that as well. So, before we kind of get into the pathways, let's talk a little bit about, again, some terminology. And what do we mean when we're talking about motor control? And that's really what we're talking about in these descending pathways. So we talked a little bit about the spinal cord. We said that neurons that were located in the ventral horn of the spinal cord were motor neurons that sent their axons out the ventral root and then directly innervated a muscle. Those neurons are referred to as lower motor neurons. That's another name for those motor neurons in the ventral horn of the spinal cord. So basically, here's the definition. These are the neurons that project directly to the muscle. No other neuron intervenes. Now, it kind of makes sense, and I don't like this terminology, but nobody ever asked me, so even though I'm a little older, wasn't involved in naming this. Could you have lower motor neurons in your brainstem? The statement here says you can. How would you have a lower motor neuron in your brainstem, based on the definition I just gave you? Do we have any cranial nerves that innervate muscles? I know that was a block ago, but remember I said you can't forget cranial nerves yet. Got to hang on to them for at least this block and maybe a little bit into the next block. Does cranial nerve 7 innervate muscles? Sure, it innervates your muscles of facial expression. How about cranial nerve 12? Or can you voluntarily move your tongue around? Can you move your eyes around voluntarily? So any cranial nerve that has either a somatic or a brachial motor component contains lower motor neurons. Lower does not indicate where in the neuraxis the neuron is located. Again, I don't know where this terminology came from, but we live with it. Learn the definition. Lower motor neurons are the neurons that project directly to and innervate your skeletal muscles. Some are in the brainstem, some are in the spinal cord. Does that make sense to everyone? Okay? If you lose your lower motor neuron, is my muscle going to have any tone? I have nothing to make that muscle contract if I pull away its innervation. And so when you lose that, that's referred to as a flaccid paralysis. There's no tone at all. And that's why I took out number 6, because we'll talk more about that in block 3 when we talk about how the motor system works. So, again, lower motor neurons in the ventral horn of the spinal cord or cranial nerve. These neurons innervate voluntary skeletal muscle. If we have lower motor neurons, probably we have some upper motor neurons. And indeed, we do. And upper motor neurons, these are pretty much confined to the cortex and the brainstem. These are neurons in our cortex and other areas of the brainstem that project to and synapse either directly on those motor neurons or on interneurons that will influence the motor neurons. Okay? So upper motor neurons are basically there to regulate the output of the lower motor neurons. And if you lesion those, you have something called spastic paralysis. And that's where everything, the tension in the muscle is actually increased because you've lost some of that descending control. Again, let's not worry about that for this exam because we're going to come back to that. Okay, any questions on upper and lower motor neurons? So what we're going to focus on today are primarily, where are some of these upper motor neurons? Well, I'm telling you they're in the motor cortex, and I showed you that when we did the telencephalon lecture, and there are also some that are in the brainstem. We talked about one of those brainstem sites last week being the vestibular nuclei. Because we talked about a vestibulospinal tract. And I said those guys went down to control alpha and gamma motor neurons. And I'm not going to talk about vestibulospinal anymore today, but I'm going to do motor, well, I'll tell you what we're going to do, okay? There are, just like there were many ascending tracts, there are a lot of descending tracts. And we're going to focus primarily on what's called the corticospinal tract, or corticobulbar, the ventral corticospinal, and we're going to touch a little bit on these two, the reticulospinal and the rubrospinal. Like I said, we've already talked about like lateral vestibulo and medial vestibulospinal tracts. Okay? The good news is the motor system to me is a little easier to conceptualize sometimes than the sensory system. It doesn't need all the relays that your sensory information seems to need. So we'll see how this all works. So let's start with two really important tracts called the corticospinal, corticobulbar. Whenever you see that word bulbar, think about brainstem. So these are axons that begin in the motor cortex, and they go either all the way down to the spinal cord, or they terminate on maybe those cranial nerve nuclei in the brainstem. Just remember, here's our lateral view of these telencephalon, and these cells that are giving rise to these descending projections, these big cells, they've got to send an axon a really long way. I mean, they have to send it from the top of your head all the way down to your lumbar level of your spinal cord. So they've got to be pretty big to sustain that axon. They're primarily in layer 5 of the motor cortex. And remember, the motor cortex is this little strip between the central sulcus and the precentral sulcus. This is where all of our voluntary movements are initiated. So just like we did for the ascending pathways, I'm going to give you everything you need on one slide, and then we'll again break it down. So let's start with the corticospinal. Defined as mediating voluntary movement. I want to lift my arm, I've got to activate motor neurons in my motor cortex that send the signal down to motor neurons that are going to my shoulder muscles. In humans, these pathways are essential for our fine digital control. They do voluntary muscles everywhere, but without these neurons. Anybody know anybody who's had a stroke? Okay, think about the individual. Usually a stroke, you have paralysis on the other side, contralateral side of the body from the stroke. Did they get back some, say, arm movements and maybe some elbow movements? But what rarely you see, especially if it's a stroke that involves a large part of the motor cortex, is a return of the fine digital control. They may be able to grasp something. Those are kind of gross muscles in our forearm that let our flexors work. But to get that fine digital control, if you've lost that area of your motor cortex, that doesn't come back. And as we'll see, the reason they get some of the other movements back is because of other descending pathways that can kind of take over some of that responsibility. So, the cells of origin. Remember, for every tract, that's one of the things you need to know. The cells of origin for the corticospinal tract are in the primary motor cortex, or the precentral gyrus. Those are our two synonyms. So here we see these neurons up here in our precentral gyrus. And we see they give rise to an axon, comes down through the white matter of the cortex, enters that bundle of axons we talked about, the internal capsule, which is just lateral to your thalamus. The same axons continue down into the midbrain, into that big bundle of axons at the base of the midbrain called our cerebral peduncle. They continue down into the pons, forming those little bundles of axons that we saw on the ventral side of the pons, through the basilar pons, and ultimately they continue down and form the pyramids. So when we look at the pyramids, what we're really looking at are corticospinal axons. Okay, we're not there yet. Those same axons, when they reach the medulla, about 85% of them cross the midline at that pyramidal decussation. Okay, this is all the same. One neurons up in the cortex have sent this axon down here. About 15% are going to stay on the ipsilateral side, at least until they get further down into the cord. After the decussation, that means we actually have two different pathways. We have a contralateral and an ipsilateral pathway. The contralateral pathway is called the lateral corticospinal tract, and we'll see why when we will be looking at some cross sections today. And the one that stays ipsilateral stays in the same position as the pyramid, which is ventral. So that's referred to as the anterior corticospinal tract. We're almost there. And then, once they get in the spinal cord, depending on whether they're concerned with upper limb, trunk, lower limb muscles, they synapse on the motor neuron. Or they may synapse on interneurons that are in the ventral horn. Look, no synapses, no relays. One continuous pathway, all the way down. And then our motor neuron, that's our lower motor neuron, will then go out to innervate the skeletal muscle. So you got the whole pathway right here on this slide. So let's look at it using some cross sections, using some diagrams. Okay, we've looked at this cross section when we talked about the diencephalon. So here's a structure. There's the lateral ventricles sitting dorsally here. Maybe I didn't label it. Here's the third ventricle. So what structure is this? Well, first of all, what part of the brainstem is it part of? Is it part of the medulla, the pons, the midbrain, the diencephalon? Good, it's part of the diencephalon. Which part of the diencephalon is bordered by the lateral and third ventricles and a huge fiber capsule called the internal capsule? I'm starting to get you prepared for the next exam. The thalamus. Okay? Classic view of the thalamus with its borders. So, those axons that came out of the cortex funnel down here into the internal capsule. Next place they're going to go is the midbrain. And there's that big cerebral peduncle. And the corticospinals, corticobulbars, I should have said the corticospinal and corticobulbars at this point are running together. They're both running through the internal capsule. They're both coming now into the cerebral peduncle. And they corticospinals occupy about that area where that red box is. We'll talk about what these other axons are in that area. Let's stay with corticospinal for a little bit. So now we've moved down into, where are we? Remember, that's cross-section. Where am I?
The pons.
Good. We're in the pons. And what happens is those descending axons kind of get broken up into little fascicles by these crossing axons of pontine neurons, by the nuclei, the pontine nuclei themselves, but these bundles of axons that sit ventrally are still our corticospinal axons. Then, here's our rostral medulla, here's our caudal medulla, our classic, here's our anterior median fissure, here's the pyramid, and we identified that the pyramid was made up of axons, and those are the corticospinal axons. Continuing on now. When we get to about the level where the medulla and the spinal cord are starting to transition, we see that about 85% of the axons that were in the pyramid will cross over to the contralateral side. And notice, they're not just crossing over like this. They're not just going straight across. As they cross, they tend to go dorsally and laterally. And they're going to wind up, it's a bundle here and a bundle here. And that's basically going to become our lateral corticospinal tract because of its position. The axons that don't cross just stay right here where the pyramid was. And they're going to be called then the anterior corticospinals. And they're going to stay ipsilateral until they get a little bit lower in the spinal cord. Questions? Concerns? So, ventral view of the brainstem. Those corticospinals began up in the motor cortex, which right now is lying down on the surface. We see them here peek out at the level of the cerebral peduncle. They enter the pons, they form the pyramid, and then a whole bunch of them cross over. Okay, just looking at it from the side. If I had a lesion that damaged, let's call, because I'm looking at the screen, we're going to call this the right side, this the left side. Actually, it's the other way. This is going to be the right side, this is going to be the left side if we flip the brain back up. Okay? So if I lesion the axons, say at the level of the cerebral peduncle, or the pons, or the rostral medulla, would I have deficits on the right side, or the ipsilateral side, or the contralateral left side?
Contralateral.
Good. It would be on the left side. Right? You've got to draw this out and make little cuts, because what you say, okay, my lesion is here, but ultimately, where were these axons going to terminate? So anything below that cut degenerates, and its ultimate target were motor neurons on the contralateral side. What if I made the cut down here in the spinal cord? Would my deficits be ipsilateral or contralateral? Then they would be ipsilateral, because they've already crossed. They're always going to those motor neurons on that side. It just depends on where you make the cut, or where you have the damage. Like I say, if you draw it out and just say, well, if I disrupt it here, well, yeah, those axons were going over there. So ultimately, that's where my deficit would be. spinal cord. There actually is a somatotopic organization of the body. And it turns out that motor neurons that are going out to distal muscles, like our hand, our wrist, our forearm, are primarily going to be located laterally in the spinal cord. And as we move more medially, we're going to have motor neurons that are going to be involved in innervating more proximal muscles, like our arm, our shoulder, ultimately our trunk. Same thing for lower limb. Feet are going to be out lateral, ankles, leg, knee, area, your thigh muscles. So, kind of think about this person just standing there in your spinal cord with his trunk in the middle and his arms outstretched, or his legs kicking out. Okay? Okay. So let's just look at the spinal cord a little bit. Now, obviously, this is not a distinct pathway that I can see in this image. There are other techniques, and when we do the motor lecture, I'll show you some other techniques that will verify that where this red dashed line is, that is where those corticospinal axons wind up after they cross the midline. That's why it's called the lateral corticospinal tract, because it's sitting down here in our lateral funiculus. The anterior corticospinal axons, remember I said they stay in the position of the pyramids? So they're going to be located primarily in the ventral funiculus. Ultimately, when they get to their target, here's these green axons. These represent the anterior corticospinal tract. When they get to their target, they ultimately do cross over. Don't ask me why. We just know this is what happens. Okay? So this red is coming, these are axons that are coming all the way down to lumbar 4. The blue axons are coming here to cervical levels of the cord, so those are more concerned with upper limb. The red axons are more concerned with lower limb movements. So some of these axons are going to be peeling off of that corticospinal tract as you descend from cervical to lumbar levels. Okay. Questions? Go ahead.
So for the anterior axons, they do cross over just much later.
Yeah, the anterior do cross. They just don't cross until they get very close to their target neurons. Other questions? Okay, now here's something of interest. Here's midbrain. You have this huge cerebral peduncle. And I said those corticospinals only probably take up that part of the cerebral peduncle. And that kind of corresponds to what we would see in the medulla, the pyramid. So where are all these other axons going? I got a whole ton of axons here and here that don't seem to be continuing on down into the medulla. So what's in between? What's between the midbrain and the medulla? I can be real patient today. Good, the pons. So do you think that maybe a bunch of these axons might be leaving that tract, that bundle, and terminating on structures that are in the ponds? Some of them have come off here. So if I was down in the ponds, let's just think about a couple of things. What might they be terminating on? Well, I told you at the beginning, we have lower motor neurons and cranial nerve nuclei. Are there any cranial nerve nuclei in the ponds? Like what? Seven? Yeah. Facial motor nucleus. Any others? 12. I'm going to believe I heard that. Humor me. 3 is probably more midbrain, but they would have, some of those axons will actually come off and go up into 3, so that if I tell you to look one way or the other, your medial rectus muscles, or look up or down, you could voluntarily move them. Okay, so let's now talk about the corticobulbar tract. These are axons, by their name, are not going to continue on down into the spinal cord. They are going to terminate at various levels of the brainstem. Again, it's not a term I came up with, but we just live with it. So, basically, let's look at where they might go. This is kind of the summary diagram. You can blow up individual parts. Well, one of the places they could go is to motor nucleus of 5. What are they innervating? And you guys have your lunch today while you were waiting for the class to start? Right, the muscles of mastication. And those were voluntary muscles, right? You had to decide how hard you wanted to bite something, how soft you wanted to grind it down or not. So, some of these axons that are, see, here's our corticospinals coming down into those little bundles. But some of those axons are coming off, and they're going over here to motor 5. Some are going off to our facial motor nucleus. And these, like the corticospinals, these are primarily contralateral projections. So, you want to make a face, you want to smile, or frown. Some of those axons left and are innervating those neurons in the facial motor nucleus. We get down to the rostral medulla, and we've got the hypoglossal nucleus. And they did, for whatever reason, they're not showing them on here, but in addition, you would have abducens for moving your eyes laterally, voluntarily. Branches would be going to those motor neurons. And finally, they're going to go to that nucleus ambiguus, which we can't see. But remember, the nucleus ambiguus is where we're going to find the branchial motor neurons that innervate our pharyngeal and laryngeal muscles. And that should not say, oh, I see, it's saying 12 because it's going up to 12 there. Never mind. I thought it was saying 12. And probably some of 11. Okay? So there's where some of those corticobulbars are going. But it doesn't seem to me, you got this huge cerebral peduncle and you got maybe 4 or 5 cranial nerve nuclei that are getting input. So there's got to be other targets for these axons that are coming out of the motor cortex. Okay? So, where else might they go? Well, so here's some of the cranial nerve nuclei that we just talked about. Other targets for these descending axons, we looked at it in the midbrain, that big nucleus that kind of sits just dorsal to the substantia nigra, called the red nucleus. And as we'll see in a later lecture, that's a nucleus involved in cerebellar control of movement. So the cortex is giving input to that nucleus. Probably the bulk of those axons are terminating on neurons in the pontine nuclei. Again, these are nuclei that are related to cerebellar function. Basilar pons is a huge structure, so you're going to have a lot of input from the cortex onto those neurons. And then finally, there's also cortical input to neurons that are located in that diffuse area that we haven't really defined very much, called the reticular formation. Okay? So a lot of that cerebral peduncle is involved in sending motor information to various brainstem nuclei. So let's look first at that reticular formation. And there are neurons in that area that appropriately give rise to a tract called the reticulospinal tract. Okay. So, I'm not going to show you that tract on a cross-section, but there are columns of neurons that extend basically from the pons down into the medulla. Notice again, they're in that area we call the tegmentum. And this area, this reticular formation, has multiple functions. One of those functions is to send axons down to motor neurons in the spinal cord. Okay? So, these neurons in the reticular formation, as it says here, get motor input from motor neurons as they descend through the brainstem. That input to the red nucleus, there's also a tract, which I'll talk about at the very end, called the rubrospinal tract. We're looking now at the reticulospinal. We're not going to worry about tecto, and we've already talked about vestibulo, but there are a lot of other tracts that come down. Okay, so the particular area that projects to these reticular neurons is called the premotor cortex. And the premotor cortex, just for now, is where we plan movements. And notice they're sending axons down that synapse on neurons in this reticular formation. The reticular neurons send their axons down pretty much ipsilaterally until they get to the end. But they descend ipsilaterally, again, in that ventral funiculus. So we had vestibulospinals there, we had anterior corticospinals, and now we have these reticulospinals all in that ventral funiculus. When they leave the tract, they're synapsing primarily on more medial motor neurons. So, very similar to the vestibulospinal, they're really much involved in controlling trunk movements. Okay? Actually, we didn't talk about vestibulospinals, did we? but we will at some point. I'm doing 2 courses at the same time at just slightly different paces. Reticulospinal axons, here's their important function. They're going to terminate, they give off collaterals at multiple levels, and they coordinate and stabilize movements across different joints. So what does that mean? If I'm reaching for something, well, I gotta kind of have my trunk stable, and the reticulospinals will contribute. But more importantly, what you guys are doing now, you're either typing, you're writing notes. What they're doing is they're stabilizing your shoulder muscles so that your hand can move freely. It's not all loose and wiggly and going wherever it wants to go. It's being held in a particular position. So they're very good at contributing to movement by stabilizing our more proximal muscles. Okay. Last track is that rubrospinal. And again, here's our precentral cortex. I mean, the corticospinal is down. It doesn't have its little collateral, but there should be a collateral going here to the red nucleus. And then the red nucleus, that neuron sends its axon, it crosses immediately. This one doesn't descend ipsilateral. As soon as the axon comes off, it's crossing the midline and descending contralaterally as a rubrospinal tract. And we'll blow this up in a little bit. So cells aboard. So what's the red nucleus pretty much doesn't go below the upper thoracic cord. So it's primarily involved with upper limb movements. And it also has a propensity for synapsing primarily on motor neurons that are going out to flexor muscles. It'll excite the flexor muscles and inhibit the extensors. So holding, reaching, flexor means increasing the angle. It begins in the red nucleus, again, descends to the spinal cord, and let's look at it here. Okay. So here's the red nucleus, the axon crosses immediately, descends contralaterally. What's interesting, its location, when it gets into the spinal cord, is just ventral to the corticospinal tract. And in some species, it's thought that the rubrospinal tract is very important for controlling some of these movements. And then as the corticospinal tract evolves, it takes over a lot of those functions. But here we see it. So let's look at these green axons over here. So here's our corticospinal tract. This would be the area of the rubrospinal. I don't know why I didn't make them red, but he didn't. And the axons are coming out. Notice they don't go all the way lateral. They don't go all the way medial. So it's not necessarily trunk they care about, but it's more kind of proximal limbs, and especially the flexors in those proximal limbs. There we go. Make that a little bit larger. Corticospinal, rubrospinal, kind of coming to these motor neurons that are kind of in between our digits and our trunk muscles. But this is a completely contralateral pathway. Yeah, if you get below the cervical cord, maybe upper thoracic, so our proximal limb muscle, again, involved in providing some of that stability. So, red nucleus does get input. So there's another cortical bulbar axon coming off, terminating in the red nucleus. It gets input from the cerebellum. And as we'll see, the cerebellum is involved in saying, here's what my motor cortex wants me to do, but how do I do it in a coordinated fashion? So they're kind of converging on some of these neurons to initiate some of that coordination. And then we see these axons descending down into the spinal cord itself. So I put together a little table here, summarizing those 4 tracks. Obviously, we focus primarily on the corticospinal and corticobulbar tracks. We'll come back to the reticulospinal in an upcoming lecture. We'll actually come back to all of these tracks, because down the road, we are going to talk about how do we control motor activity. And look more at the circuitry involved. But for now, let's just focus on bigger picture. Let's just get the axons to where they need to go. So I'm going to really get you guys out of here early today, but that's kind of intentional. I didn't want to give you a lot of brand new information. The descending tracks are pretty basic. So, questions?
When you asked the question about the lesions, I know that's not on the exam, but when we talk about where it's affected, is it relative to where the cut is made or relative to where the point of origin for the nerve is?
Okay, put your mask down just for a minute.
So for the lesion questions, do we